Okay, good morning, good afternoon, good evening, everyone, wherever you might be tuning in from, and welcome to this week's Science Talk from the United Nations University Institute for Water, Environment, and Health. It's a pleasure to be here with you today. My name is Dr. Rohit Ramchandani, and I'm currently UNU-INWEH's Fellow in WASH and Behavioral Science. I'll be stepping in for our host, Miriam Axel, today, and I'm honored to introduce our distinguished speaker, Professor Amir AghaKouchak. Professor AghaKouchak is the lead for water, climate, and infrastructure risk at UNU-INWEH and a globally recognized expert in hydrology and climate extremes. His research spans droughts, floods, compound and cascading hazards, and the critical intersection of climate variability with infrastructure and societal resilience. His work has significantly advanced our understanding of the complex and interconnected risks that are posed by climate change, and his insights have been instrumental in shaping policies and strategies for sustainable water management. Today, Professor AghaKouchak will be discussing a paradigm shift in drought monitoring, moving beyond traditional hazard-focused assessments to an impact-based approach that integrates the broader effects of drought. This means looking not only at meteorological and hydrological conditions, but also at how droughts translate into real-world consequences on agriculture, energy, food security, and even employment. So he'll be exploring the concept of anthropogenic drought, examining how human activities interact with climate dynamics to shape water availability. And importantly, he'll address the challenges that stand in the way of implementing impact-based drought monitoring, from data limitations to gaps in existing models. So with that, welcome, Professor AghaKouchak, and we look forward to the conversation that will follow as well.
Hello, everyone, and thanks for the generous introduction. For the record, I did not write that intro. Thank you so much. I'm truly honored. Today, I'll talk about impact-based monitoring of droughts and other cascading hazards. Of course, what I present is a collection of many different studies that were led by students, postdocs, and collaborators that I've had the honor to work with. Most of them are listed here. Before I start, let me go over some basic terms. We have different drought definitions. Meteorological drought refers to deficit in precipitation. Agricultural drought is often defined based on deficit in soil moisture. We have hydrologic drought. We define it based on deficit in runoff or groundwater or even reservoir storage. There are other types, like snow drought specifically focuses on deficit in snow. Socioeconomic drought focuses on events, drought events that have kind of specific socioeconomic impacts because of lack of water. And a broader term, anthropogenic drought, that focuses on events caused or intensified by human activities, and it includes all kinds of different human activities that can have an impact on water availability. But a good example is Lake Urmia. We have seen significant changes in lake area and volume. So that's the blue line here. And if you look at surface water withdrawal, the red line, you see when this significant increase in water withdrawal started, lake levels went down significantly. So the surface water withdrawal is the anthropogenic part. The purpose was to divert water for irrigation and farming to create jobs, but there was this significant environmental impact. In fact, if you look at just meteorological drought, that's the curve down here, you see there are all kinds of wet and dry periods, including long drought and long wet periods, historically and more recently. Even the recent wet periods did not cause any sort of significant recovery because of the significance of the anthropogenic factor. So when we are looking at anthropogenic drought, we look at two different aspects. We always look at other factors, including meteorology, precipitation deficit, runoff, and so forth. The anthropogenic part includes broadly two different elements. One is what we can associate to water management, increasing water demand, or expansion of the agriculture sector, water withdrawal, and so forth. There is also a climate change dimension. Anthropogenic activities means more emissions, and emissions can potentially change your rainfall pattern. So it will have an impact on meteorological drought. So it's a complex process and involves many different dimensions. Today, I'm going to focus on how we can translate drought information to drought impact and move toward impact-based drought monitoring. So I'll talk about different types of examples. Let me start with snow drought. A few years ago, we worked on Sierra Nevada specifically, and then later globally, on changes in snow. We noticed that there are years when we have above average rainfall, but in summers we end up in really extreme low flow conditions or drought condition. And we thought this must be because of maybe deficit in snow. So this is a slide that summarizes one of our past studies. We looked at different issues, including center of mass of snow. If you have a lot of snow, usually that center of mass is lower under extreme conditions, let's say warming condition or low snow condition. Usually that snow is at much higher elevation. And in addition to snow mass, we also looked at snow water equivalent. So these PDFs, these are probability distribution functions of snow water equivalent or SWE for different levels of warming. So -1 to about +1 above average to about 1 degree below average. So these PDFs are for a specific time of the year. In case of California, April 1st, that's when we measure snow as an indicator of water availability. That's kind of end of the snow season for us. So you can see that even 1 degree plus minus makes a big difference in terms of probability distribution of snow water equivalent. And if we connect the dots in these PDFs, you can create a line, and it shows that 1 degree of warming means about 20% change in snow water equivalent. That is very significant. In many places, we rely on snow, including California. So 20% change in snow water equivalent can translate to significant downstream impact in the agriculture sector or in water resources and even industries. Now, by the way, how did we get these curves? So if you build a relationship between two variables, let's say snow water equivalent and precipitation, and you create a two-dimensional probability space, you can extract PDFs across different lines. So for example, you pick two different thresholds, each correspond to, let's say, 1 degree below average, 1 degree above average. If this is a two-dimensional probability space and you extract values along a line, you get a one-dimensional PDF. So that's what we're looking at here. So we did the same thing with central mass of snow. So again, colder years, snow mass, center of mass is lower. We have snow at lower elevations, but in warmer years, snow is mainly at higher elevations. So this helped us to kind of establish and develop and release the first global snow drought product. So these are hotspots of snow drought. These are places where changes in snow can significantly impact water availability. These are the areas, these are basically hotspots of the world. There are many other places where you have sensitivity to snow, but in these places, snow is a big fraction of water use. So this includes Western US, also some parts of the Middle East and Central Asia. And based on this information, we developed this global snow drought indicator. So it gives you kind of information about deficit in snow. Again, this is not replacing meteorological drought. If you want to properly monitor drought, you still have to look at your meteorological drought from precipitation perspective, but we suggest that we have to look at snow separately. So these are some example outputs. The scale is the so-called D scale. So D4 means exceptional drought. D0 means abnormally dry. And we have also a similar pattern scale for wet conditions. So this dataset is available globally, and you can download the data if you're interested. It's publicly available. Also, there is a code for extracting data. And in the rest of my presentation, I show how we can use this kind of information or similar snow deficit information to kind of link this information to impacts. Again, historically, when it comes to drought mapping or drought information, we create maps like this that show geographical location of drought. For example, here, looking at drought in the US, we see these areas under drought. The reality is drought impacts propagate to other regions. There are places in the world where we produce a lot of food, and this food moves to other countries. If you want to do impact-based drought monitoring, we need to go beyond just geographical location of drought. So this is a follow-up study that basically tried to translate snow drought to impacts in the agriculture sector. So we use a global model to kind of estimate gridded runoff, as you can see here on top, and having all components of the water cycle, you can extract what fraction of runoff comes from snow melt. So that's what you're looking at here. And of course, if you have a model, not only you can look at historical data, but you can look at future projections from many different models under different, say, warming scenarios, let's say 2 degree plus or 4 degree plus. And you can look at change in snow melt, runoff, and so forth. So now imagine we have this kind of information, and now we want to connect that to impacts. So with a global model, we have global gridded runoff, and fraction of that comes from snow melt. We also have global information on irrigation, and we can kind of estimate what fraction of irrigation water is coming specifically from snow melt. This is a global assessment for different basins. You see where you have a large fraction of irrigation water coming from snow melt. And in some cases, the source of snow is in another country or very far away. For example, snow in Hindu Kush or in Central Asia basically feeds rivers that go through multiple countries and even into areas that are relatively dry. And if you remember the map I showed about hotspots, again, you see this one is kind of consistent with the previous one. Now, another important data set that's available is production of different types of foods from different countries. Not only production, we also have imports and exports from different countries for different types of crops. Now, I'll talk about imports and exports and combining them all together later. But for now, let's just focus on basically country scale crops. And again, remember, we have global data sets that provide information on, again, country level irrigation, what fraction comes from snow, and a lot of other variables. Now, this means that for each type of important crop, we can look at all countries collectively and look at, again, what fraction of irrigation water for these crops is coming from snowmelt. This is, again, a global analysis, but barley production from all countries are combined into one single column here. And you see on the y-axis, we have time of the year. So you know that the kind of crop seasons vary from country to country, especially from northern hemisphere to southern hemisphere. So time is also important. And if you want to translate impacts, you need to account for deficit in different times of the year. For example, if you have deficit in January, you see that the impact might be relatively small, but if this deficit continues toward the end of the snow season, at least in the northern hemisphere, we quickly see significant impacts. In this specific case, the impact is change in water available for irrigation. And of course, that will translate into impacts on crops. So again, in this case, we are putting everything together. This can help us to look at all droughts across the world and potentially link everything to potential changes in different crops. We can say maybe there will be a reduction of around, say, 10% in this specific crop. And of course, different countries use different fractions of, say, barley, wheat, and so forth. And then we can even put that in perspective in a relative sense. I'll show you an example in a moment. Based on the snow deficit information that I showed you earlier, we created this kind of snow hazard index. Remember, I showed you some hot spots. Again, these areas highlighted here reflect those hot spots. So this kind of snow hazard index, or SHI, is very simple. We look at change in snow melt. Specifically, we look at the fraction we use in irrigation. So we call it snow melt consumption ratio times change in alternative water resources. What happens if you don't have enough snow? Usually what happens, you look for an alternative source. So you extract more groundwater. You try to bring water from another basin. So this alternative can also be roughly estimated with models and also with data we have on water withdrawals. And of course, we can do this under different scenarios. Remember, we have a model, so we can do this for different levels of warming, like 2 degrees or 4 degrees of warming. Now, I mentioned a figure that kind of combined the impacts from irrigation perspective on crops from all countries. Now, you can also do that at basin scale or country scale. For larger river basins, again, we have information on irrigation and snow. So we can do this kind of analysis this time for a specific crop and its distribution around the world. So here, top left, for example, we're looking at wheat. wheat is produced in different countries. In some places, sensitivity to snow is very small, like most part of Africa. But there are places where you have significant sensitivity to snow because a large fraction of irrigation water comes from snow melt. And again, sometimes the basins that we are looking at are low-lying basins far away from mountains, but we know that water moves from high elevations, from mountains, down to areas where it is eventually used for irrigation purposes. So here are 3 examples for 3 major crops, but again, we can do this for many different crops. So keep this in mind, and later I'll kind of connect this to impacts. So by the way, this paper specifically mentioned here looks into, basically does this translation of drought information to, in this case, impact in the agriculture sector through maps like this. A few years ago, with the help of colleagues, we put together this global data set of water, food, energy, based on, again, global information we have from different countries on food production, water use, energy use, specifically for the agriculture sector. We know that agricultural irrigation accounts for a large fraction of global water consumption. It varies from one country to another, but typically it's around 80% or more in most places, not everywhere. Also, this agriculture sector, including the food supply chain, uses a large fraction of our energy. So we thought that if we put this data together, we create opportunities to analyze these data sets, we can potentially find inefficiencies. So there is this Nexus of Food, Energy, and Water toolbox. It comes with a database, and the toolbox allows you to quickly process the data. So let me show you some outputs, specifically with a focus on agriculture sector. Again, our focus here is linking deficit or drought information to agriculture sector. Top left shows water withdrawal in form of volume per person per year. So it's per capita information. And if you look at water use in general, you see the hotspots, the red areas are places like the US and the Middle East. So these are places where a large fraction of water withdrawal is used in the agriculture sector. But now let's normalize this to the amount of food produced in each of these countries. That's the lower figure, bottom left. So again, the same information in the top panel is now normalized by tonnage of food produced in these countries. You see that the perspective changes. For example, in the US, if you look at the total volume, it's very high, but when you normalize it by the amount of food produced, it goes below even global average. But in some places like the Middle East, it's very high in terms of total. It's also very high in terms of water used per tonnage of food. This means in some areas, we have significant inefficiencies that can potentially be improved. The top right figure shows a similar figure with a focus on energy consumption in the agriculture sector. Again, you see that hotspots are places like the US and China, but both of these countries produce a significant amount of food. So when you normalize by, in this case, kilowatt hour per kilogram, the energy use goes below average. Many countries remain very high, including Egypt and some cold countries like Canada, Japan, Norway, because they use a lot of energy for their agriculture sector. So this shows that there are potentially inefficiencies that can be improved. So for better visualization and relative comparison, we put these data to a graph in this form. Here, the y-axis is a water withdrawal for the agriculture sector, and the x-axis is energy per unit agriculture production. So similar information as here. So here, energy in kilowatt hours per kilogram of food, this is per year. And in terms of water, we're looking at volume, again, per kilogram of food per year. So here, the dotted lines are global averages. And the color bar here is per capita production. So this is tonnage of food produced per capita in that specific country. So we see that there are countries that produce a lot of food in this scale, and they are below global average, but there are countries that produce very little food, but they use sometimes even twice global average energy and water. These are places where we have significant inefficiencies that can potentially be improved. Now, we talked about food production and irrigation water use and also energy. Ideally, we want to kind of translate drought information to cascading impacts. So a few years ago, we put together a team, worked on this notion of compound and cascading events. We put them in these 4 different categories. Specifically, I want to focus on temporally cascading or temporally compounding events, because if you think about drought and some deficit in food, let's say, this deficit will propagate around the world through trade, through exports and imports and change in storage. So there is this time dimension or temporally compounding dimension in impact-based drought monitoring. So again, traditionally, when we look at drought, we look at maps like this. For example, in this case, drought based on standardized precipitation evaporation index. So our focus is on geographical location of drought. So we have deficit in this specific place. We can look at future projections in this example, and again, looking at deficit. But we know that food moves from one country to another. This kind of information is available from different sources, including FAO, Food and Agriculture Organization. Also, US Department of Agriculture has a Foreign Services Office that keeps track of global imports, exports, and storage. So that information is available. And in the nephew dataset I mentioned earlier, in that global dataset, we have all this information by different crops. So for each crop and each country, we have export, import, and storage over the years. In some countries, we have longer record, 50 years, 60 years. In some countries, we have shorter record, maybe 10 years or only 20 years. But the network of these changes or movement of food from one country to another doesn't change drastically from one year to another. This means that even with relatively short record, you can kind of track food and develop a model that can simulate how food goes from one country to another. So This is an example of movement of food from different countries to one specific place, in this case, Egypt, and the fraction of food that comes from different countries. So this allows us to investigate what if scenarios. What if there is a major drought in the US and you have disturbance or some kind of interruption in export to this country, this specific country? What if there are two different droughts independent from each other? Let's say drought in the US and drought in, for example, Russia. It can happen. It has happened before. And you see there are, in this case, it's actually Ukraine, and that also exports food to Egypt. Now, potentially different droughts in different locations can have compounding impact with a certain time lag. The interesting thing is that it takes, so first of all, thinking about, remember snow and snow melt, usually there is a lag time from the time snow falls until when it ends up into river system and used as irrigation water. So there is a lag time there. And also this translation to local impacts. If there is drought, it takes a while before we see some kind of deficit in food availability. This allows us to maybe even provide predictive information. Now here, I'm showing one example where we looked at drought in a specific place. This is 2002 drought in Canada and the US. And we translated the impact in terms of deficit in calorie supply. What does it mean? Remember I showed you this global map of different food, different crops, different products, like wheat, barley, canola, and different types of products. Imagine you combine everything into their equivalent calories. So each country has a certain amount of production and a certain amount of export and net storage. So the net amount, the available food, we have that information for different crops, and there is this kind of average calorie for each crop. So if you combine everything together, you can create an indicator of overall food availability. So this means that in this specific drought, obviously there was no deficit in the US or Canada at all, but there are deficits in some other countries in Africa. These are places where they import food from those sources. And even when you look at these deficits, there is significant disparity. There are places like Saudi Arabia where you see deficit, but Saudi Arabia imports way more food than they need. So they have a huge surplus of food. Even if there is a deficit, usually does not translate to significant impacts. But there are some other places like Algeria and many other African countries that don't have much surplus. The buffer is very, very small. This means that if there is deficit, that deficit will translate into impacts. That kind of impact translation is a little bit difficult. We're working on it now, but we can basically link that to even potentially health impacts. One thing I'd like to emphasize is that the trade network also can be used and translated into a measure of resilience. That's work in progress. There are countries that only import from one place. And because of that, if there is a change in the source, that country may be impacted significantly. A good example in the literature, there are publications that show because of ban in export of food out of Russia in 2010 because of a major drought. Food prices went up in Syria, and it contributed to the conflict and social unrest. Not that it caused it, but it probably impacted to some extent. But there are countries that import from many different sources, and those places are more usually resilient against changes. I remember I mentioned that we can look at fraction of food coming from different places. Again, this curve here at the bottom shows wheat imports in one specific country, Egypt, and these are sources of food. You see that Egypt imports food from the US, from Ukraine, from Russia, from different places. So this yellow bar is Ukraine. A model like this can even allow you to investigate the compounding impacts of droughts and even non-climatic events. What if there is a major drought in the US, for example, and also war in Ukraine? Or there is a major drought in Russia and war in Ukraine. You can see that these events are independent from each other. One of them is kind of climatic, the other one is non-climatic, completely independent. But when it comes to food availability, they can have compounding impacts on each other. Those types of compound events are very difficult to model or to investigate in any other way other than data-driven analysis like this. So that's one of our kind of projects, work in progress, looking at what kind of drought and non-climatic droughts can cause significant deficit and impacts around the world. So for each country, we have this kind of information, and that allows us to develop this extreme what if scenarios. Some other potential dimensions when it comes to impacts, we have evidence that fires are increasing in terms of size. This is data from California, but also fires are happening at higher and higher elevations. This is elevation of fires. We have fires that are happening at 3,000 meters from sea level. These are areas that used to be too cold, too wet to burn, but now they are burning. Because of that, snow may be impacted because these are high elevation fires, fire in mountains, and later in the year, these areas will receive snow. And snow in burned areas where there is little canopy will have very different dynamics. It will be exposed to more solar radiation and potentially it melts faster. Faster snow melt means higher flood risk in spring and at the same time higher drought risk in summer. So this kind of fluctuation between flood and drought can have also impacts in the agriculture sector. Remember when we were talking about impacts, so even fires can have, even if your snow does not change, large scale high elevation fires can cause changes in snow melt. And these processes are complex, but we have kind of models that can simulate these conditions and hopefully translate them into impacts. This is also statistics of change in burned areas. This is from California, but we have similar patterns in many parts of the world. So with this increasing size of fires, we have had fires in California, individual fires larger than 1 million acres. So fires of that scale will certainly have impacts on snow, and those impacts will be propagated into different sectors. We also have evidence of change in extreme precipitation. This is one example of data from different kind of scales, the whole world, Northern Hemisphere, this is North America. So more extreme precipitation also means potentially more floods, and even more rain overburned areas. So rain overburned areas can also cause problems, downstream problems in the agriculture sector. So these are different types of cascading hazards and impacts that can potentially happen. Currently, if you look at existing drought monitoring and prediction systems, they only produce maps like this one, top right, deficit in snow, deficit in rain or soil moisture, and they are all geographical. What we are missing are, we put them in two different categories. One, cascading hazards that are not specifically happening at the same time, but they are related. We call them drought-related cascading hazards. Drought can increase chance of fires, and fire means there is a chance of rain over burned area, even landslide, debris flow events. And again, remember, fires can potentially increase chance of snow over fires, rapid snow melt, and floods. So these are very different types of hazards that happen in different scales, but they are related. So for this reason, in a recent paper down here, we argue that we need to go beyond monitoring of individual hazards and combine systems that we have developed for different types of hazards, droughts, floods, heat waves, and fires, because they are all interconnected. And more importantly, we need to translate the impacts for different types of sectors, for example, agriculture sector. And I showed you one example here, specifically on snow and agriculture, but we can do this for potentially other sectors. Now, very briefly, some of the models we used for data analysis are based on these two packages. Both are available online. So MVCAT and MAST. So the first one, MVCAT, is designed for analysis of relationship between different types of data, including hazards like temperature, snow, or different types of flood drivers, or drought and heat waves. And the second one specifically generates hazard scenarios. There are different types of hazard scenario models built in that you can use for different applications. In both cases, source codes are available, but we have also a version with a graphical user interface. For those who don't want to deal with codes, you can load your data, pick your model, or let the model pick the right type of model to describe relationship between your variables. So if you're interested to use it, but you have problems with getting it to work, you're welcome to reach out. I'll be happy to help. With that, I hope I have convinced you that there are opportunities to go beyond just simply drought monitoring, considering deficits in meteorological and hydrologic variables. There are opportunities to translate that to agriculture sector, energy generation. We have done work in that space too, and I did not present it here, but we can translate change in water availability to change in hydropower. It's relatively straightforward. It's actually easier than even agriculture sector. Potentially, this can be done for different types of industries that rely on water. So the opportunity is there. It's an important area, but we have to spend a lot of time and effort in making this happen. Finally, one more time, I'd like to acknowledge my research group. These are some of them. They are the ones who do the hard work. I'll be happy to take any questions you may have. Thank you.
Thank you very much, Professor AghaKouchak. for a very fascinating presentation, very important talk. We now have some time for questions, and I'd like to invite our audience to share their thoughts. Please feel free to type your questions into the chat and the Q&A. In the meantime, while we await some of those questions, Professor, if you could speak about the challenges in impact-based drought monitoring in terms of what are the most kind of immediate steps that governments or organizations can take to integrate this approach more effectively?
Very good question. The main issue is...
sorry, Professor, if you could just, your screen right now is on,
Stop sharing.
If you stop sharing, it'll okay. Work better.
Sure.
Yeah. Thanks.
Better now?
Yes.
Great. So the main issue, I think, is data availability. So ideally, to simulate these impacts and track the impacts from one country to another, you need data on food production, on exports and imports. Again, we have rough data available from FAO, from US Foreign Services, but we know that FAO data are not very reliable. There are errors and uncertainties. And more importantly, we don't have, in many places, we don't have reliable data at basin scale. And in large countries, like in the US, case of the US, Russia, China, you can have drought in the western part of the country and flood in the eastern part of the country. So if you have just aggregated data, it's really hard to translate impacts to that specific sector. So ideally, we need kind of food production, energy generation at basin scale to be able to do this kind of analysis with high confidence. The biggest issue is right now is data availability.
Fantastic, thank you. Please. We have a question in the room.
Okay,
Sure.
Appreciate Professor AghaKouchak for very good presentation. My question is about the ecological drought. I would like to know your idea about this kind of drought and how we can, develop appropriate indicators to monitor and predict ecological drought, and also how we can integrate it with, for example, for water management and other.
Sure.
Thank you so much.
Yeah, so ecological drought doesn't have one single definition. You can define it based on basically your needs and opportunities. For example, this could be based on forest health. That's one potential dimension. Can be defined based on lakes and wetlands. We have one work in review right now specifically that defines drought based on lakes and reservoirs. So it can be defined differently for different purposes. There is no universal definition on ecological drought. The main issue, again, when it comes to ecosystems, our observations are relatively limited. We have satellite data. That's the good thing about satellite observations. You get bird's eye view of forests and wetlands, and there are indicators already available at that scale. But if you want to get down to really small scale ecosystems, we don't have a lot of data, and it gets very difficult and complicated. So it can be defined based on different indicators and variables. And I think that area has a lot of room for research. We don't have a lot of publications in that space. There are a lot of papers on change in vegetation color based on NDVI and so forth in response to drought. But when it comes to actual ecological impacts, we have a gap between, let's say, change in NDVI to actual impacts.
I can maybe ask one more. Given the increasing frequency of kind of compound hazards, where droughts are triggering, wildfires and floods and economic disruptions, how can we enhance interdisciplinary collaboration to kind of better predict and mitigate some of these risks?
Good question. So if you want to integrate your hazard monitoring systems, remember one part of this impact-based, ideally, one big part is to not just monitor droughts, but to include other related hazards, including fires and floods. That by itself means you have to bring experts from different fields, experts that may not even communicate with each other on regular basis. But to build a system like that, there is no way around this. You have to have a big team of experts with diverse backgrounds to be able to build that kind of monitoring system. Now, if you want to link that to impacts, you need social scientists, economists that can translate changes in hydrologic and climatic variables to impacts. And that's the hard part. If you look at everything that we have right now, when it comes to hydrological variables, climate variables, we have different sources of data. We have ground-based data, we have satellite observations. When it comes to impact field, the field of impacts, we have very little data. Most of our data sets are aggregated over large scales. Even if you want to extract drought information for major events, we have fragmented data. The US has a database only for major events. EU has another database, again, only for major events. The rest of the world, I haven't seen any impact-based data set available. So you have this huge gap. And to fill that gap, this is something that I cannot do. People with my expertise cannot do. You have to work with political scientists, you have to work with impact experts, economists, and more importantly, social scientists that work in this space to be able to create the baseline data you need to do impact-based analysis.
Yeah, that's fantastic. I mean, I really see that as one of the strengths of what we're kind of doing at United Nations University, is kind of bringing so much of these, different interdisciplinary kind of expertise to the table together to really, look at some of these challenges together and then put that in front of, policy decision makers and the like. So I see a few questions in the chat here. So this one is from Anonymous. It seems that in the Middle East, we have lost time. It means that the countries could not adapt themselves to the new climate conditions. Do you think that it is possible to reduce the effects under the current conditions?
Yes, I think still we have opportunities that we have not exploited. So if you remember the figure I showed about water use and energy use in many countries, including in the Middle East, water use is significantly higher than many other places. This means there are potentially opportunities. Demand management, for example, is really important. We have control on it. Yes, we don't have control on droughts or precipitation, and there may be changes that are outside our control. But when it comes to water management, we have control on it. So with smart decisions, there are opportunities to adapt. But what we don't see is proper action from governments. There are different types of issues. Not all countries in the Middle East are the same. Some have more political problems than others. Some others have more management issues, but I think we have significant opportunities to develop adaptation strategies.
Wonderful. We have a question from Maria Dewey from UNU-INWEH. And she asks, regarding impact-based forecasting and monitoring for drought, which timescale would you consider as the most relevant, like in thinking about the impacts in terms of timescale? And then her second question is towards having impact information in agricultural drought and crop loss to warn farmers. Which impacts do you think are the most important to explain or visualize, and which drought indicators are relevant for use at that level?
So also I noticed there's a question about slides. Yes, I'll be happy to share. You can email me, or I can share it with UNU, and maybe you can share it with participants. About time scale. So if you look at current drought prediction models, we can't even predict drought reliably more than 2-3 months. So even dynamic model simulations that give you 9-month predictions, we know, even model developers know, that those predictions are not reliable at all. So in terms of dynamical model simulations, we have limited predictability, but we have a very good near real-time data, and we can do short-term predictions. Now, if you predict drought in the next 2 months, relatively reliably, which is possible, or near real time, the translation to food impact usually happens between 3 to 9 months, depending on where you are in the world and what kind of import and export you're looking at. So that's the kind of lead time you have on the impacts. Yes, we don't have much lead time on the actual drought prediction, but we can have significant lead time on the impacts, because once the drought happened, then you know there will be some deficit. And the question is where that deficit will go. How does it propagate into the system? So the lead time, I would say, on the impact, the lead time you get from 3 to 9 months is even more than the lead time you get from drought prediction itself. Now, the second question about the types of indicator and data, it varies significantly for different crops, for different countries, for even different technologies they use. You may need different types of indicators, so we cannot simply generalize it. And what I mentioned today may not be that relevant to individual farmers, but more those who work on policies for countries, make decisions at country scale on imports, exports, buying more, less, and things of that nature.
Wonderful. I see that we're almost at time here, so I'd like to just sincerely thank Professor AghaKouchak for sharing his expertise with us today. And thank you all for your thoughtful engagement. If you'd like to continue the discussion or explore these topics further, I encourage you to connect with UNU-INWEH and Professor AghaKouchak's work. All of our science talks are made available on our YouTube channel at youtube.com/user/UNU-INWEH. And we look forward to seeing you all at our next science talk. These are held weekly on Wednesdays, and we look forward to our continued engagement. Thank you, Professor, and we'll see you all next time.
Thank you so much.